Good morning, everybody. Sorry I'm late. All right, let me get the thing in here. We're going to continue on with what we were doing, and that was looking at Module 5, which is naming. I think what many people forget about Module 5 is that what you're required to do here is make sure that the positive and negative side of everything balances out. And once you've got that concept under control, it's not too bad. Okay, let's have a look. Start share screen. Okay. So we had been working on all of these binary compounds. I'm going to do a little bit of a summary just to get you back up to speed with where we were. Can you all hear me, by the way? Make sure you
Yes.
can. Thank you.
Yes, we can hear you.
Good. And I've been working my way through the soft chalk, which I think is probably one of the better ways to go through this stuff here. All right, let's do some examples here just so you can be brought back up to speed with what we were up to. So I made the point that, let me see, make sure everybody's actually got their video up here. Whoops. Oh, good. Everybody's got their video up. That's great. All right. Okay. So we were, let me just put a summary here of what we know. We've got the type 1 cations. And these charges do not change. That's kind of what's most important about them. And what we're talking about here is group 1, which is 1 plus, group 2, which is 2 plus, and aluminum, which is 3 plus. There are a couple of others, but I'm not going to worry about them. These are the main ones that I want you to be concerned about. Type 2 cations. These charges can change, or they do change. Now, the consequence of all of this is that these don't need Roman numerals. Because the Roman numeral is about the charge. And these do need a Roman numeral. And again, the Roman numeral is the charge on the cation. So I think that's really the most important point that people sort of forget about. So I'm going to put some examples up here. We'll do Na2S. We'll do TiS2. We'll do PbCO3, and we'll do Ca3N2. Okay. So what I had said was, you look at, you want to look at the cation first and determine what it is, whether it's a type 1 or a type 2. And we can do that by looking at the periodic table. Actually, I can do that from here. Let's go to page 2 here. So there's your standard periodic table here. So if we're looking at group 1, group 2, or aluminum, now if it's in any of those, then that's really going to have a huge impact on the name, because then we don't need a Roman numeral. But if it's any of the others, we do. Now, since sodium is in group 1, then we know it's just going to be sodium sulfide. Now, one of the common questions people have is, well, how do you know that there's 2 sodiums? Well, the thing is, if you were to take this back, you'd say, well, S is 2 minus and Na is 1 plus because it's in group 1. And then you say, well, how many sodiums do I need to balance that? And it has to be Na2S. This is why we don't need the Roman numeral in the name. Does anybody have any questions? Anybody have any questions? So you got TiS2. Now the thing is that Ti is not in group 1, group 2, or aluminum. It's over here. So it's one of the transition metals. So I draw a picture of it where I have 1 Ti and 2 S's. The S's are in group 6, which is -2. So I do -2, -2, makes it -4, which makes it titanium +4, because again, everything has to balance out. So the name of this then would be titanium -4 sulfide. And here you can see that we do need the Roman numeral here, because we don't know what charge titanium has, because it's not one of those type 1 cations. The type 1 cations, the charge never changes. The type 2 cations, the charges can change, which is why we need to include the Roman numeral. So that should clear up any concerns anybody has about excuse me, about when to use a Roman numeral or when not to, or why some things have Roman numerals and some things don't. Does anybody have any questions? The other ones that don't change are zinc 2+, cadmium 2+, and silver plus. But usually, I mean, you won't see these in any of the testing that we do, but I'm just telling you that these are considered to be type 1s as well. And if ever you're in a situation where you're trying to remember that, you can see aluminum, you can see zinc, and you can see silver. You can see they go on a diagonal here, and cadmium is down around here as well. So you can see it goes 3+, 2+, 1+. As we go down here. So these 3 here are also considered to be type 1s as well, because those charges don't tend to change either. However, you won't see any of these in any of the tests that you do. I'm just trying to simplify things a little bit so you don't have to remember as much, but that's something else that you can be aware of. Does anybody have any questions at all?
The reason aluminum, zinc, and silver don't change just because they have set electrons, correct?
Well, I have set charge. In other words, yeah. They only lose a set number of electrons in order to become the charge that they are. So zinc always loses 2. It won't lose 1, it won't lose 3. It'll always lose 2 and never anything else, which makes it a type 1. Very much like sodium can only lose 1 electron. All right, any other questions? The other point that sometimes people run afoul of here is how to deal with polyatomic ions. And I made a big point about this the other day. So you got CO3, and CO3, there's only one of them. Now, the reason we know there's only one of them is because there's no parentheses around it. So that means it's CO3, and that's -2. And again, you'll always have access to a polyatomic ion sheet, so you'll know what charge these have. So you've got carbonate down here, that's a -2 charge. So we know that CO3 is -2, and there's only one of them. And then we've got the Pb, which has to be +2 to match it. And because lead is one of these that is one that doesn't, the one that has a charge that can change because it's in the type 2 area, it's not one of the type 1s, then I know that the name is going to be lead 2 carbonate. And it's necessary to have the 2 here because lead is not one of these type 1 cations. And again, the 2 is for the charge on the lead, not how many leads there are. Does anybody have any questions? Now the last one I have here, Ca3N2. We look at Ca, we see it's in group 2, so we know it's a type 1. So the name just becomes calcium nitride. Again, no Roman numeral here. And you might be asking, well, how do you know there would be 3 calciums and 2 nitrogens? Because if we have the charges, we know Ca is 2+, and we know N is in the -3. I'll move this up a little bit. N is -3. You can see that there's no way that just one of each would make that even. So we know we need 2 N's and 3 Ca's to make that match. So one tip I can give you is you can always multiply these together. You say 2 times 3, that's 6. And ask yourself, well, what do I need to get to +6 and -6? So it'd be Ca3 and 2. And that's how we're doing that. That's why you don't need any indication in the name of how many calciums there are, how many nitrides there are. Does anybody have any questions about any of this?
Yeah. I do actually.
Yeah.
Do we have? Does this module include the like the special types of naming, sulfite, like that? Is this module, or is that?
No, it is this module. But the thing is, you've got the polyatomic ion sheet available to you during the test, so you don't have to memorize any of that. You see, you'll have it all here.
Thank you.
Yeah, and I showed you this last time when we were looking at the actual tests that you'll be taking, how the sheets were actually embedded within the test, so you'll be able to access them without having to do anything else. That's why I don't allow people to use any other resources, because all the resources are within the test. Is that okay?
Yeah, that was what I was gonna ask that next. Is this provided? Yeah, thank you.
Okay, does anybody have any other questions so far? Okay. Now I want to move on and take a look at naming of acids. So acids, these are a little bit tricky. I will admit this, because I don't like the way that the naming has been set up for acid. Now I didn't make this up. This is just how people name them, and I think that there really should have been something else going on here when they did this. But this is the story with the naming of acids. When we say acids, The acid part is the H part. So if something is H plus as the cation, then it's going to likely be an acid. Now, sometimes it may not be named as an acid, and in any question that asks for the name of an acid, I will always put acid in parentheses next to it so you know it's an acid. And if it's an acid, then you're saying, well, H plus is the cation. Where it gets confusing is how we deal with the different anions that go with the H. So we have two kinds of anions that we talk about. We've got the single element anions, which are the ones that have, well, you guessed it, a single element, like F, S, or Br, as I have in this example over here. And then we've got, or the other possibility, which is these polyatomic ions. Now you can see the difference between a single element and a polyatomic ion. A single element anion has just one element, whereas a polyatomic ion has many more atoms in it. So you've got nitrogen, oxygen, sulfur, oxygen, Cl, and oxygen. But as such, they're named differently. The single element anions are named hydro something ic acid, hydroic acid, hydroic acid. The hydro does not mean hydrogen. This is why I don't like this naming system, is because the hydro is often mistaken for hydrogen, and it isn't. The acid part is the H plus. The hydro part tells you it's a single element anion. So why is this important? Well, let me show you for instance here as to why it's important. I'm going to give you an example. Let's say you've got HBr, and over here we've got HBrO3. This one here is a single element. And this one here is polyatomic. Does anybody have any questions so far? So the name of this one is hydrobromic acid. Where the acid part is the H plus. And this one here is called bromic acid. So you can see why it's important for us to be able to distinguish between these. I mean, if somebody came up to you in the street and asked you for the structure of hydrobromic acid, you'd want to be sure that you said HBr and not HBrO3. Likewise, if they said, well, look, I need the structure for bromic acid, look, I'm sure this happens to you all the time. Then you'd be able to say HBrO3 and not HBr. I mean, this could be life changing for you. You just never know. Somebody could have some sort of emergency and they need to know what the structure of one of these acids is. You need to be able to tell them. Does anybody have any questions? This is why it's important. I'm just telling you why it's important that we distinguish between the names, why we have different kinds of naming. And the hydro is telling you it's a single element anion. That's all. Now, with regard to the polyatomic ones, there's two rules here that are going to be important, and I've got them here. If the polyatomic ion ends in the suffix ate, then it becomes ic acid, because, like in this case here, BrO3 is called bromate. So that becomes bromic acid. Anything that ends in ite becomes us acid. So I've got a couple of mnemonics here. It was icky, so I ate it, and ite and us, like lighthouse. So that's a way you can remember that. So you can see I've got some examples here, like HNO2 is from nitrite, that's nitrous acid. H2SO3 is from sulfite, that's sulfurous acid. And HClO is hypochlorite, which would be hypochlorous acid. Does anybody have any questions about the naming of acids? Anything at all? We also need to deal with the compounds of two nonmetals. Let's go back to the periodic table here. I want you to remember that we know where the nonmetals are because of this steppy business that you'll usually see on a periodic table. Sometimes you'll see it, sometimes you won't. But in this instance, you can see the steppy business here. And we know that everything on the right side of the steppy business is non-metallic. Everything on the other side is metallic. It's usually not too hard to remember that. But as such, what happens is when you've got compounds of two nonmetals, they don't form in the same way as the compounds we've been looking at so far. When we're dealing with compounds of two nonmetals, we tend to be dealing with covalent bonds, which involve not the giving and taking of electrons, but the sharing of electrons. And what that means is that neither of the species involved in the two nonmetals actually physically takes on a charge. They share their electrons instead. Now, as such, what that means is that we need to find a way to name these that allows us to say how many of each there happen to be. So I made a big deal of this earlier when I was talking about some of these other examples, how the positives and the negatives had to even out. Well, here there are no positives and negatives. So we have to rely on how many there are in order to come up with the correct name. So P2S5 would be diphosphorus pentasulfide. And these are the prefixes that we use, and you're actually provided with these. You don't have to remember them. Many of them you already know. Tri, diameter, tricycle. Tetra, well, I can't really think of a tetra example for you, but like a Tetra Pak for milk. If you've seen a milk carton, those are called Tetra Paks. They open up with a four-sided figure. Penta, pentagon. Hexa, hexagon. Hepta, like heptathlon or heptagon. Octa, octagon or octopus. Nona, well, nona sounds like 9. Deca, 10, decade. And undeca and dodeca, 11 and 12. Does anybody have any questions so far? So the other rule that we have here is when there's only one of the first element, we tend not to use the mono. That's because a lot of these only have one of the first element. So P2S5 would be diphosphorus pentasulfide. Carbon CO2 would be carbon dioxide, not monocarbon dioxide. But if you look at CO, you'll see that's carbon monoxide. We do need to use the mono on the second one. Does anybody have any questions? Does anybody have any questions? I've got a whole bunch of others here for nitrogen oxides as well. So that's all the situations we're dealing with here when we're going from formulas to names. Now we can also go backwards from names to formulas too. And as you'd expect, actually, I think this is probably easier than going the other way. Now the reason is, I'm going to put down some examples here, and you'll be able to see why this isn't that difficult. Okay, so let's see. So looking at the first one, I'll just do these in order. We've got lithium sulfate. What we do is we say lithium was 1 plus, and that means now we've got SO4 is 2 minus. Now the reason we know was 2 minus. The reason we know that lithium is 1 plus, go back to the periodic table, and lithium is in group 1. So we know it's 1 plus. And then you're asking the question, well, how many of each do I need to make this even out? Well, then it becomes Li2SO4. Does anybody have any questions? Anybody have any questions? All right, chromium 3 nitride. Now, in these situations, when you've got the Roman numerals, even easier because you don't have to go hunt down the charge. You know it's immediately 3 plus, and you know nitride because it's in group 5 is -3. So the answer here would be CRN. You just need one of each to even out the charges. Does anybody have any questions? Next one, calcium phosphate. So calcium is in group 2, so it's +2. Phosphate, PO4, 3 minus. Now the 2 plus and the 3 minus don't even out, so I know I need to figure out how many of each I need to make that even. 2 times 3 is 6. So calcium 3, PO4 in parentheses 2. So that'll be +6 and -6, and that'll even out. Does anybody have any questions? Sodium nitride, Na plus, N3 minus. And again, the question we're asking is how many of each do we need to make this even out? We need 3 sodiums, so it'll be Na3, N. Any questions? Lead 4 sulfite, Pb4 plus because of the 4. Sulfite, SO3 2 minus. That's off the polyatomic ion sheet. With this one, it's important to note we've got -2 and +4. We need 2 of the -2s to even that out. So it'd be Pb SO3 2. Any questions? All right, so that's pretty much what we do. Let's look at a couple of names of acids here as well, and maybe some names of non-metal compounds as well. So let's say we've got Chloris acid, hydroiodic acid, hydrofluoric acid, perchloric acid. So these are all acids, which means we know what the H, we know it's H plus. So let's look at Chloris first. So what we need here is we need the polyatomic ion sheet. I think it's on this page here. And Chloris what we do is we look at this and say Chloris, well, Chloris comes from chlorite, and it's a polyatomic ion. I know this because there's no hydro in front. So Chloris comes from chlorite. Now chlorite is over here ClO2 minus. And we would need one H plus to balance that. So it'd become HClO2. Any questions? Hydroiodic means that's a single element and it's iodine. So it'd be I minus, which means we need one H plus, which would be HI. Any questions? Again, hydrofluoric. The hydro indicates that the F is its own element, F minus, and we need one H plus to balance that, HF. Any questions? Perchloric, there's no hydro in front of it, so it must come from the polyatomic ion sheet. Perchloric comes from perchlorate, which is over here, ClO4 minus. So I'll write that down. Perchloric comes from perchlorate. HClO4. H plus ClO4 minus HClO4. Any questions? Okay. And then the naming of carbon tetrachloride. So carbon tetrachloride, that would be just CCl4. The other one, trinitrogen pentachloride, N3Cl5. Does anybody have any questions? Now remember, on your polyatomic ion sheet, you'll have the prefixes down here from 1 to 12, so you don't have to memorize any of them. All right, does anybody have any questions? Now let's take a look at the Module 5 assignment. Now this is a bit time consuming because there's a lot of questions on it, but once you get the hang of it, you can get it done pretty quick. If it's taking you a long time, it means you don't really understand what you're doing. That's the problem. Now what it's doing is that, let me look at another example here. Yeah, something like Li2O. What you're looking for is the charge on a single one of each. that you're given. So what I mean by that, if you're given Li2O, you're only after the charge on one lithium. If O is -2 and lithium is +1, then the answer there would be lithium plus. The reason I do it this way is because this is what the naming is all predicated on. It's all predicated on what the name of one of each cation and each anion is. I mean, that's how it works. That's why I require that kind of work here. Let me see if I can find another one. So FeI2 the charge on one iodine is -1 and the charge on the Fe is 2 plus. So if you're asked for the anion and cation, then you answer accordingly. Does anybody have any questions? Nobody has any questions about that. Okay, fair enough. See if I can get back out of this. Doesn't look like it. So there's 80 questions there. Has anybody done it yet? Just out of curiosity.
I have.
How long did it take you?
About, I think,
About what?
half hour?
About half hour. Yeah, that's usually what people take on it. It's about half an hour. Some people complain, say it's just too many questions, but the whole point is to get you used to being able to find a charge on one of each, which is what the naming is based on anyway. So yeah, while people don't like it, the better you are at it and the more you understand it, the less time it takes.
Yeah, I remember my last chem class had a 200-word test on this, or 200 question one. It took about an hour and a half to complete just to make sure it was all correct.
Yeah, that's right. Okay, but that one's 80, so it's not as bad.
Yeah, not at all. No.
All right. So this is what the practice and the credit quiz look like. So what you'll notice is that you'll have a bunch of things here, and one of the answers is actually none of these. So you need to be prepared for the eventuality that none of these will actually come up as an answer. Sometimes it does, sometimes it doesn't. So just because it's there, it doesn't mean it's not used, but it doesn't mean it's always used either. So you really do have to know what you're doing here. So strontium nitride. So strontium is 2 plus. Nitrogen is -3, or nitride is -3. Sr3 and 2 would be the answer. And you can see that that is not on the list. So the answer would indeed, for this one, be none of these. Does anybody have any questions? Chromium 3 bromide, Cr3 plus, Br negative, CrBr3 is what you come up with. And that one is actually listed there. Hydrofluoric acid. So again, remembering your rules here. So A H and H plus and F minus. Again, the hydro indicating that fluorine is by itself. H, F will be the answer there. Nitrogen disulfide, that's one of your two non-metal situations. Yeah, that's the thing. Whenever you've got these prefixes and stuff involved, then you know it's a two non-metal situation as well. And nitrogen disulfide, NS2. Anybody have any questions? Yeah, that's always a good clue. If you see these prefixes, you know it's two nonmetals. I think that can be helpful. MgSO3, what the name of that is, magnesium sulfur. So MgSO3, so magnesium and sulfide. Again, pick that up off the polyatomic ion sheet. Does anybody have any questions? All right. Well, then you've got plenty of fun to be had here, and that's the thing. This is again why it's important to make sure that you are doing work as you go and not waiting until the last minute. Most people, most of you you'll wait until, probably at least 2/3 of you will wait until the night before or the day before it's due to start doing this. And a lot of you are just simply not going to get the work done. And that means that you're going to end up not getting as good a grade as you would have hoped, just because you were too procrastinating, too unwilling to do this, get stuff done early. I don't know. It's not my. I guess it's not my personality type, but I don't like to leave things to the last minute. But a lot of people seem to. I'm not sure why. I'm not sure of the psychology behind it, but there it is. Procrastination has consequences. All right. Does anybody have any questions?
Nope.
So these are the kinds of questions, the ones we've been going through just now on this practice quiz. These are the kinds of questions you're also going to see on the test as well. The only resources you should be using or are the ones you would use on the test. This would be my suggestion. And I would say make sure you've got a periodic table in front of you, and possibly, well, actually, you don't even really need the list. You don't even really need the names of elements because it's multiple choice. So you see the name there anyway. So you don't even really need that. That is provided to you with the test, by the way, but you don't really need it. And the other thing is the polyatomic ion sheet. So you should just have those two things, periodic table, polyatomic ion sheet. That should be all you need in order to be successful with this. All right, any other questions? Okay. Well, what we'll do is we'll get a start on module 6 then. Let's take a look at how the schedule is looking here so we can get an idea of what's going on. So the situation that we have here, if we're just looking at the schedule as we've got it, today is Monday, so we're here at 1:25. This is Wednesday, of this week. We are actually starting on module 6 now. So we'll actually have probably, today we'll have we'll get a little bit of module 6 done today. We'll do the bulk of module 6 on Wednesday, and then we can have maybe a very small portion of module 6 will be on next Monday. Then we're scheduled to do a review, which means just going through the test. The following Monday, so that's 2 weeks from today, where you'll be doing, that's when, oops, sorry, I didn't mean to do that. Sorry about that. I didn't mean to click on that. That is when the module test will be due. The homework that what I've been talking about will be due on Sunday, 11:59 p.m. The other thing is, I think, yes, there is also some extra credit that you can get too for test 1. And that is by completing the sample module test, the one you actually have to do. You do that on Sunday and get 80%, then you can get 5% of extra credit there as well. So if you miss out on doing some of the homework, that can be a good way to make it up, is by doing the extra credit. But you can't do the extra credit on the day the test is due. It has to be the day before. So you have to be a little bit organized. Does anybody have any questions? Anybody have any questions? There won't be a Zoom session on the day that the test is due. Okay. Anybody got any questions at all? Anybody got any questions? All right. Well, let's go to module 6 and we'll get a start on the okay, so we've got balancing chemical reactions. We'll start with that. So this is a fairly easy example of balancing, is this one here. Here. The idea here with balancing is that the only thing you can ever do is put numbers out in front, because all you're doing there is changing the moles. So if you've got this kind of situation, I'll go ahead and do this in an example. It's very simplistic though. If you had Fe plus O2 gives Fe3O4, what you can't do is go Fe3. You can't do that. What you can do is you can do 3 Fe's plus 2 O2 gives Fe3O4. So that's allowable. But this is not allowable. Let me point something out to you here. If you've got, I'll tell you why this is important. So Cl2, if you've got Cl2, that would indicate it's 2 Cl's joined together by a bond. If you've got 2 Cl's, that's 2 separate chlorine atoms that are apart from each other. Does anybody have any questions? That's the difference. That's why we can't balance by putting in subscripts. We can only balance by putting in numbers in front of coefficients, is what we call them. Now, when we balance these, I often use or ask for what's called the sum of coefficients. So let's look at, well, we'll do this as an example here, what the sum of coefficients for this one would be. The sum of coefficients is pretty much exactly what it sounds like. It's 3 plus 2, and then often there won't be a number out the front here, but that will count as a 1. So this would be 3 plus 2 plus 1, which would be 6, would be the sum of coefficients. Does anybody have any questions? So in the soft chalk here, I've got a pretty nice exercise here that illustrates that, I think, pretty nicely. So let's go through. We'll do this, and I'll show you some examples of balancing here. Let's look at V2O5 plus Ca gives CaO plus V. So when you're looking at this, what you'll do is, I always, for this one, it doesn't really matter as much because we only have one of each thing on each side. But if I'll show you some examples where there's certain times you wouldn't start with something. Like if you had an oxygen here and an oxygen here, you wouldn't start with oxygen. If oxygen's in lots of places, then you don't start with oxygen, you start with something else. For this one, I might start with the vanadium. That's a 2 there, so I'll put a 2 in front of the V. I've got a 5 here with the oxygen, so I'll put a 5 in front of the Ca. But the 5 now covers the Ca and the oxygen, because the 5 is now going to cover everything after it, which means that this is going to need 5 as well. I'll stop here for a second. Does anybody have any questions? If I did the sum of coefficients on this one, it would be 1 plus 5 plus 5 plus 2, which is 13. Any questions? So H2SO4 plus HI gives H2S plus I2 plus H2O. I would never start with hydrogen here because hydrogen is just in too many places. I might be inclined to start with something else like iodine. We've got 2 I's over here, so I'll put a 2 in front of here to try and balance that out and then sort of see where I'm at. Now, as far as the oxygens go, I see I've got 4 oxygens over here and 1 over here. So I might be inclined to put a 4 in front of the H2O and see where we are at that point. So now, as you can see, we've got 10 hydrogens on the left side and we've got 4 hydrogens on the right side. And it's this one is a little bit tougher to come up with because we have to now sort of juggle all of these different things. But because the I is single over here and is not with anything, it's just I2 by itself, I can see that that would be a good target to try and adjust. Adjusting anything else is going to be problematic, I think. So what I would do is I've got what amounts to 10 on this side. If I was to change this to 8, that would mean now I've got my 10 hydrogens on both sides, but now I've got 8 I's over here, which means I can adjust this by putting a 4 in front of the I2. So you see, it does become a dynamic process in order to balance something. The sum of coefficients on this one would be 1 plus 8 plus 1 plus 4 plus 4, which would be a total of 18. Does anybody have any questions? Anybody have any questions? That is a more difficult one, I will admit. Let's see, V2O5 plus HCl gives VOCl3 plus H2O. So we've got 5, so 2 on the V's. We'll put a 2 in front of the V like this. I would never start with oxygen here because oxygen is in too many places. So V, I'll leave the oxygen alone. Let's look at the CLs. We've got now 6 CLs, so I have to put a 6 in front of here. And then we can look at the hydrogens and see where we're at. We've got, let's see, 6 hydrogens, 6 hydrogens, 6 CLs, 6 CLs, 2 Vs. So it's only the oxygens that are left for us to look at. We have 2 oxygens already on this side. If I put a 3 in front of the H2O, it turns out that that gives us the 6 hydrogens we need, but it also gives us a total of 5 hydrogens as well. So 2 plus 3 is 5. So you've got to be careful about that as well. Make sure you're counting all the oxygens. Does anybody have any questions? All right, like I said, that's a good little exercise to do. And I do have a video that actually shows you exactly how to balance every single problem in that little exercise there. So that can be very helpful as well. Does anybody have any questions? Anybody have any questions? All right, I think we'll leave it there for today, and we will continue with the fun on Wednesday, and we'll be looking at predicting reactions of acids and bases, and also the double displacement, the dreaded double displacement reactions. All right, if anybody wants to stay and ask me any questions, they're more than welcome to, and I will see you soon. All right, thanks everybody.
Thank you, Professor.
Thank you, Professor.
Thank you, Professor.
Thank you.
Have a nice day.
You too, bye-bye.